So, good day everyone. It's Marjorie Ganyola again from BSED Math 3B. You can remember, we have here the table M which represents my geometric model called M double square algebra. And as you can also remember from our first video, we have proved that this table forms a group structure because it satisfies all of the conditions. First is the closure, then the associativity, and lastly the existence of identity and inverse element for all. Also, as shown on the second video, we've got 19 subgroups from this table. One for the improper subgroup or the group itself, 17 for the proper subgroups with an order of 8, 4, and 2, and lastly, another one for the trivial subgroup that contains only the identity element. So our agenda for this video is to determine whether the group is cyclic. So to classify whether a subgroup is cyclic or a group, we must satisfy the following conditions. First, it must be abelian because all cyclic groups are abelian. Second, it must have at least one generator. So what is generator? Generator is the elements that generates all of the elements in the set. First thing that we have to determine is the group M itself, also known as the improper subgroup. The first condition that we have to satisfy is if it is abelian. So as you can see in here, the table is not symmetric from its diagonal line. Therefore, we can conclude that it is not an abelian. Since it already violates the first condition, therefore it is not already a cyclic group. However, we can still check whether its subgroups are cyclic subgroups, even if the group itself is not a cyclic. Now, we have here the proper subgroup M sub 1 with an elements A, J, E, O, 8, 5, 9, and 2 under the binary operation star. So as you can see in here, the table is also not an abelian because it is not symmetric from its diagonal line. Therefore, it is not an abelian because it violates also the first condition. Therefore, we can conclude that this subgroup is not a cyclic. Next is we have here the M sub 2 with an elements A, J, E, O, 1, 6, and 4. 1, 6, 4, and 3 rather, under the binary operation star. Let us see whether it provides an abelian structure. So as based on the table, it is not also symmetric. So it is not also abelian. Since it violates the first condition, we can conclude that this subgroup is not already a cyclic subgroup. We also have here M sub 3 with an elements A, M, J, I, E, G, O, and R. So just like the first subgroup, let us see whether it satisfies the condition. As you can see in here, the table is symmetric from its diagonal line. They have the same figure. It is symmetric from here. They are symmetric, so we can conclude that it is abelian. Now let's see if it has at least one generator to determine if it is really a cyclic group. As you can see in here, A star A is equal to A, so A generates only itself, while M generates J, I, E, G, O, R, and E. Because M star M is equal to J, J star M is equal to I star M is equal to E star M is equal to J star O is equal to O star M is equal to R, and R star M is equal to A. Oh, pardon. This was supposed to be A, not E. You can just change it. Next, G only generates E, O, and A because J star A is equal to E, E star j is equal to O and O star j is equal to A. I is also with O, M, E, R, J, G, and E because I star I is equal to O star I is equal to M star I is equal to E star I is equal to R star I is equal to J star I is equal to G star I is equal to A, and A star I is equal to I. E only generates two elements, which is A and E. It's actually one element only, the identity element. Because E star is equal to A and A star is equal to E. Naulit lang. G is also with J, R, E, M, O, I, and A. Because G star G is equal to J star J is equal to R star J is equal to E star J, oh, E star G is equal to M star G is equal to O star G is equal to I, O star G is equal to I star G is equal to A, which is the identity element already because A star G is equal to J na. Next, O generates only three elements, the E, J, and E because O star O is equal to E star O is equal to J, and J star O is equal to A. And lastly, we have the R that generates O, G, E, I, J, M, and A because R star R is equal to O star R is equal to G star R is equal to E star I, E, E star R is equal to what? G star R is equal to E star R is equal to I star R is equal to J, and J star R is equal to and M star R is equal to A, the identity element already, and A star R is equal to R na, naulit na. And as you can see in here, M, I, G, and R generates all of the elements in the table. Therefore, we can conclude that our generators are M, I, G, and R. And since it satisfies both of the conditions, we can conclude that M sub 3 is a cyclic subgroup. Next, we will be delving on the proper subgroups with order 4 or 4 elements. First, we have the M sub 4 with elements A, J, E, and O under the binary operation star. So as you can see in here, in the table, from the diagonal line or the purple line, the table is symmetric. Therefore, it is abelian. All we have to do now is to check whether it has a generator or at least one generator. So A, we're starting with A that generates only itself because A star is equal to A already, the identity element. Then J that generates E, O, and A because J star J is equal to E star J is equal to O, and O star J is equal to A. Then E that generates A only because E star E is equal to A, the identity element already na, because A star E is equal to E. Naulit na. And lastly, we have O that generates E, J, and E because O star O is equal to E star J is equal, E star O is equal to J, and J star O is equal to A. So as you can see in here, J and O generates all of the elements in the table. So we can say that J and O are the generators of this subgroup. And this subgroup, M sub 4, is a cyclic subgroup. So now, we have another proper subgroups with order 4 or 4 elements. The M sub 5 with elements of AJ 1 and 6 under the binary operation star. The M sub 6 with elements AE43 under the binary operation star, M sub 7 with elements A, E, 8, 9 under the binary operation star, and M sub 8 with elements A, E, 2, 5 under the binary operation star also. So if you are curious on why did I put them as one in the screen, it is because all of them are isomorphic to each other. If you can still remember the Klein for group ba yun? It is isomorphic with this. It's like 1 of M sub 5 is mapped to 4 of M sub 6 to 8 of M sub 7 and 2 of M sub 8. And 6 of M sub 5 is also mapped to 3 of M sub 6, 9 of M sub 7, and 5 of M sub 8. So as you can see in the tables, they are all abelian since they are symmetric on their diagonal line. They are symmetric. Now let's see whether they have at least one generator since they already have satisfied the first condition, which is abelian, because all cyclic groups must be abelian. So in M sub 5, all of the elements generates only the element A or the identity element. Therefore, there are no generator that generates all of the elements. And since they are all isomorphic to each other, all of them are the same. They all of the elements in the other table are all of the elements in the other table generate only one element, which is the identity element. Therefore, we can conclude that there are no generators in these subgroups and they are not a cyclic subgroup because they might satisfy the first condition, however, they violated the second condition, which is having at least one generator since they have no generators. So next is we have here the subgroups with two elements or order two. So the same with order 4 subgroups kanina, I showed them all in one screen na lang since they are all isomorphic to each other also. All of the tables from M sub 9 to M sub 17 has the same image. It's just that the elements are different. Since from the previous topics, we have proved that all group table with two elements are abelian. Therefore, all of these subgroups are abelian. And also, they are symmetric din kasi. Next, let us see whether they have at least one generators. So, from our M sub 9, A star A generates only A, while 1 star 1 is equal to A, and A star 1 is equal to 1. Therefore, 1 is the generator. So it is the same as the other table since they are isomorphic. They have at least one generators. Therefore, we have proved that all of them has at least one generator and they also prove that they are abelian and they satisfy the conditions of a cyclic. Therefore, all of the subgroups with order 2 are cyclic. Next is we have the trivial subgroup that contains only the identity element. In this case, A is its own generator as A raised to any power including 0 is still A. Therefore, a group with only one element is indeed a cyclic. And the table M representing the M double square algebra model contains 19 subgroups and 12 of them are cyclic. So here are the cyclic subgroups that we have proved. So we have 11 for the proper subgroup and 1 for the trivial subgroup. And that is all. Once again, I am Marjorie Canyola from BS EdMath 3P.